appreciate the invitation to give this seminar. And as David said, I guess I've been studying analog gravity a lot in the last decade or so. And I'm always interested in trying to learn something about real gravity. I'm ambitious in that sense. I don't just want to do an experiment just because it's fun and it's somehow similar to a black hole or an expanding universe. I want to actually try and think, did we somehow learn something about the real universe? Get some kind of a hint or something. So anyway, so here, this is an experiment. I usually do black holes, acoustic black holes. And I'll be talking about that in a colloquium next week. But this is something different. This is something I did in a sabbatical 5 years ago and, in Paris in the group of Content Glorieux. And we used a fluid of light to simulate the expansion of the early universe. So I'll present this talk of analog cosmological particle creation in an ultra-cold quantum fluid of light. So I'll explain more what that means, but the systems where one can see these effects would be a Bose-Einstein condensate. That would be a typical system to use this very cold, ultra-cold gas of atoms. And there was an experiment in a Bose-Einstein condensate, as well as an experiment in a pair of trapped ions, where one can see this particle creation, sort of like in the early universe. And our system is different in that we have this quantum fluid, and we'll see it really on the quantum level, this production of these particles. So, what is cosmological particle creation? So this is a graph showing the universe, the growth of the universe. So this is the size of the universe as a function of time. And at first, the universe grew very rapidly, perhaps it's thought during the inflation period by a very large factor. And then there are various other phases. Particles were created, and there was a plasma, and then there was recombination, and we're over here, way over there somewhere, present day. So if one looks at the CMB, the cosmic microwave background, and one looks at the anisotropies and isotropies, and one decomposes it into multipoles, into spherical harmonics as a function of L. Then one was looking at the temperature of the radiation that one's seeing, and one sees a power spectrum with these oscillations. And supposedly, what we're seeing here is in this period where there's this plasma, this photon baryon plasma, there were acoustic modes, sound waves in this plasma. And it's the result of these sound waves that we see this power spectrum with these maxima. And there was supposedly a time of observation where the plasma recombined, and the time of last scattering. The last time that photons, they became free and they just started propagating, and we see the photons here today. So what is the usual description? If you look in, I don't know, a typical article on the subject of cosmology and asking where do these acoustic modes come from? There's sort of this microscopic, what seems to me like a long microscopic description with many steps that all happened in the very early universe, the first few 100,000 years of the universe. And it starts with inflation, where during inflation, all modes get extremely redshifted during inflation. So here's a mode. It's some mode crossing across the entire universe here. And as the universe grows, the modes also get stretched. And so their frequency goes down because the wavelength is getting longer. So because they're stretched so much during inflation, they all get stretched to zero frequency. Any mode that, say, you have some populated mode. Say here at the beginning of inflation, there's some mode with some population, some mode like a photon mode or something, and it has some population. It'll get stretched so by such a huge factor that you can say its frequency was zero and it no longer exists. So that means all the modes are empty during inflation. So inflation redshifts all modes to zero frequency, zero population. But the modes do have quantum fluctuations. So even though the modes are all empty during inflation, there are quantum fluctuations of these modes, like vacuum fluctuations, you can call it. So as these modes get stretched and stretched, they're stretched faster than the frequency of the mode. So the inflation is so fast that it's faster than the frequency of the mode, and the mode can't oscillate because its frequency is changing faster than its frequency is. So the modes get frozen in. So the quantum fluctuations are frozen in. And this mode has some quantum fluctuations and they're frozen there. They can't oscillate. Now the inflation ends. And that mode starts to oscillate again because it's not expanding so fast anymore. And so now these quantum fluctuations start to oscillate again. And at the same time that this happens, that these quantum fluctuations start oscillating, particles are created. And for a different reason, the particles are created because the inflaton, supposedly this inflation is caused by this mode, this inflaton mode. And this mode damps away and creates all the particles. So suddenly at the end of inflation, all the particles are created here. And you end up with this photon baryon plasma of all these particles created. So now going back to our quantum fluctuations now in this mode, which are starting to oscillate, they turn into acoustic oscillations, sound waves in the plasma that has just been created. So that's how these acoustic modes come into existence. It's somehow the quantum fluctuations that were in inflation that had some interesting behavior there, frozen and unfrozen. The quantum fluctuations in inflation become sound waves in the newly created plasma. And these sound waves are created with a definite phase relationship. We'll discuss this later. These are not just random sound waves. They're sound waves that come in pairs with a definite phase relationship. And that's what makes, and that's what we see today in the sky. So that's the typical description. To me, that's very complicated and has many steps. And I mean, I'm not an expert, but it seems, how sure can they be that this is correct? But anyway, that's the standard picture. So there's an alternative description, which is very different from what I've explained so far, and it's not very well known. Many cosmologists don't ever think about this. And this alternative description is much simpler. We just say the modes at some early time have some frequency, and later, because the universe got bigger, the modes have a lower frequency. So you have modes with changing frequency. And when you have that, then these modes become populated. That's called the dynamical Casimir effect, where especially if the modes are changing at a rate which is comparable with the frequency of the mode itself, the rate of change is comparable to the frequency, then the modes very much become populated from nothing. It's a quantum process. It comes from vacuum. The modes just suddenly have a population. And this is the dynamical Casimir effect. And this is the alternative description. We just say during inflation, there was some mode. At the later time, like during the plasma, the mode now has a lower frequency. Therefore, it's populated. Now, in this alternative description, the microscopic processes are ignored. We didn't say anything about a plasma being created and all the different things that happen with modes. being frozen and unfrozen, all that stuff, we just ignore. We just say the frequency is going down, that's all we need to know. So once you have that kind of picture, this alternative description, then you can simulate it in the laboratory very easily. You just have to have a system where the modes, the frequency is changing. And you can say that's similar to the early universe. That's what we did. It would be very difficult to actually simulate the previous picture, this one where you have to have this inflation and the particle creation and all these steps. It would be, I don't think anybody's proposed actually simulating on the microscopic level the early universe that I know of. So, but we're here in this analog cosmological particle creation that relies on these papers by Schrödinger, Parker, and others discuss this alternative view. So, so mathematically, the way one describes this is with a Bose-Einstein transformation. So at an early time, the modes there's some annihilation operator for one of these modes, and it has a frequency omega A. And then at some later time, there's an annihilation operator for the later time mode, and the frequency is something else, omega B. And so then we say these operators are related by a Bose-Einstein transformation. And this says that the annihilation operator here is related to the annihilation operator here, or the creation operator for a mode with minus K. So, and the coefficients, the Bose-Einstein coefficients are alpha and beta, which are related to the change in the frequency. Now you can see if the frequencies are equal, say nothing happened really, the universe didn't expand, then alpha is 1 and beta is 0. So alpha is sort of nothing happened. It's like you just annihilate a particle K, and it's the same as annihilating annihilating one of these is the same as annihilating one of these. It's the beta that really is the mode mixing between the plus and minus K that causes entangled pairs. And the beta is only non-zero if the frequencies are different. And this is all derived in the case of a very rapid change. These expressions for a perfectly sharp change in the frequency. So once we have this Bose-Einstein transformation, we can immediately write down the population of the particles. This B, remember, is after the change in the frequency at the later time. So we could calculate B dagger B, the population, and just write it down straight from this expression. And one has these various terms with alpha squared and beta squared. And the most interesting one is here, this 1, which is the spontaneous production. This is the vacuum fluctuations producing the particles. The other terms rely on, for example, A dagger A, which means a population before the change. So if you had a population during the inflation, this term would give you a population after the inflation. But it's this special 1 term that's the spontaneous one. It happens even if you were in vacuum before. Okay, then also there's correlations. This is pair production. And so there are correlations between these pairs. That's given by this term, and it also has here it has some what we call stimulated, where these A's appear. That means it was stimulated by what there was before the change in the frequency. But there's also the spontaneous term here, the alpha beta, for the correlation. So in order to know what the population and correlations of these cosmological particles or analog cosmological particles are, we need to know the initial state. We need to know the populations or the correlations before the change in the frequency. So initial quantum fluctuations. So here we'll look at the real universe and our analog system. Before the change, during inflation, you can say. So in the real universe, we said that the modes redshift to 0 frequency. We said if there are modes that are populated, they expand so much. that they go to zero, and there are no longer populated modes. That was the real universe, the early times and the late times. And because of the redshifting, you have vacuum fluctuations only the quantum production of the pairs. Here's our analog system now that we're going to discuss. It's a laser beam, like the one coming out of this laser pointer, only a bit more powerful and narrow, much more expensive laser, narrower spectrum, and so it's propagating along. And what we're interested in is fluctuations, intensity fluctuations perpendicular to the beam. So for example, the beam coming out of here is a 2 millimeter diameter beam. And on those 2 millimeters, there might be intensity fluctuations. It might be a Gaussian profile. A laser beam is usually just a Gaussian intensity profile, but it might have some waves on it. And those are the waves that those are our particles that are going to be created. It's waves. And time for us is position along the beam, which is not really time. It's a effective time. It's position, it's z along the beam. So there might be waves at an earlier time, and then they might evolve with time, and at some later time, there'll be some other waves. Now, for this also is going to start, we're going to see that this starts out as vacuum, because there are none of these waves on our laser. Our laser is a good laser. And the laser manufacturers make some very good lasers, the engineers, and so there are no such waves. It's a shot noise limited laser. The only noise in this laser is if you shine it on a camera, you put a camera here, you'll see it's just random. Every photon picks a random square or the random pixel on the camera. There's no other noise other than the random photons. That's shot noise. So that's why our system starts out as vacuum fluctuations only.
But here we don't have any change of frequency, right? The analog system.
Not yet. The next slide will. There's no change in the frequency. In this slide, there is. So the laser beam goes through a gas, a vapor cell. So this is a closed little chamber with rubidium gas in it, and it's close to resonance. The laser is close to resonance for this gas. So this causes an effective interaction between the photons, because the laser, the intensity of the laser affects, modifies the index of refraction of the gas. And the index of refraction then modifies the propagation of the laser itself. So in that sense, photons have interaction. One photon changes the index of refraction, and the next photon feels the changed index of refraction. So this nonlinearity is causes an interaction between the photons. Somewhat.
If there would be more Poisson changes in the photons themselves, the noise is going to change.
Yes, okay. We say the ground state noise changes. Now that these photons are interacting, they're no longer just random. You wouldn't expect the same spectrum of shot noise because they're no longer random. It's a liquid now. You have a different static structure pattern if you want. So yes, it definitely changes the fluctuation.
What is a quantum fluid like?
Okay. Fluid. Now it's called a fluid of light because the photons are now interacting. So you get fluid behavior. It's not just a whole bunch of photons traveling on straight lines or that vortices or various any kind of turbulence, fluid behavior. Quantum fluid of light, because it's cold enough, it's you could say it's near its vacuum. It's near vacuum. It has very few of these waves. As we discuss these transverse waves, There are very few of those, so you're seeing the quantum effects. We'll discuss it, we'll get more into that. So, so we see we have two what are called quenches, and a quench means change in the frequency, rapid change in the frequency. So when the laser comes into the gas, first it had no interaction between the photons, and then suddenly we turn on the interactions between the photons. And that changes the frequency of these waves. So there's a sudden change in frequency over here. Then when the laser beam comes out of the gas, there's another sudden change in frequency of the wave, of the mode. So
They interact by quantum scattering.
how do the photons interact? Through it's mediated by the atoms in the gas. That one photon will change the index of refraction of the gas.
Ah, okay, that is gas.
Yes, that's and it's close to resonance. This laser beam is close to resonance. You have a significant change in the index of refraction. Well, not it's still much less than one, but a noticeable change in the index of refraction. And that affects the subsequent photons. And in fact, okay, well, I could draw, I guess I could.
Yes.
Well, okay, I won't draw. I'll just, okay. Oh, there,
If you
over there,
want, you
okay,
can, yeah.
yeah. The laser beam decreases the index of refraction. In this, but you could make the laser beam do either if you're above resonance or below resonance. We choose it so that the laser beam decreases the index of refraction. So that means, so where the laser beam is, there's less index of refraction. That's like a diverging lens. You could think a usual lens, like on my reading glasses here, this lens has higher index of refraction in the middle, so it focuses something. It'll focus this. If I shine this laser beam through the glasses, it'll focus it. We can do that. Anyway, but I'm an experimenter, so I want to just forget the lecture and let's just shine a laser beam through the glasses. But no, okay, just joking. But anyway, so but since it decreases the index of refraction, it'll cause the laser beam to get bigger. So when the laser beam goes through the gas, it decreases the index of refraction, and that will cause the laser beam to grow. And that's the interaction between the photons. The laser beam causes the other photons to expand.
Maybe a stupid question, but before the light entered in this gas, it was in vacuum, right?
Yeah, over here
Yes.
in air, yeah, vacuum, yeah.
So the index of refraction is 1. So if you
Right.
go below 1, you have a speed of light that is greater than
Okay,
1.
very good question. How does it go less than 1? What happened, I didn't mean that. What I meant was, if you had a low intensity laser beam in the gas, then it has some index of refraction greater than 1. Okay. Then you turn up the intensity and it goes down.
Okay.
Okay. So here now we're going to the analog. We're thinking this is an analog expanding universe. So over here, it's an expanding universe when the laser beam comes out, because the frequency goes down, just like when the universe grows. But we also have like a contracting universe here at the beginning, where the frequency goes up. And then we have these, we're interested in these waves. I schematically drew a wave here, transverse to the beam. And so what we're going to do is, after these two quenches, we're going to look in some plane later in time. So you could say, here's the expansion of the universe. Then you wait some time, that's until the present time, a billion years, and then you take an image. And effective time, as I mentioned, is the position along the beam. The tau is z over the speed of light. That's the effective time.
Just another quick question.
Yeah.
Compared to the early universe, where it was continuous, here it's sudden, right? It's brutal. As when we go out from the gas, the frequency brutally change.
Right.
and it's not continuous. You just look at few time, but it has already changed before, right?
Yes, well, and for the real universe, you could say you had a rapid change in the frequency, and then you just waited a really long time. Also.
Okay.
So, so what we're going to do is here's what it looks like when we shine the laser beam onto a camera. So here's the laser beam, and the various waves that you're seeing are not the waves we're interested in. That's just some noise in the imaging system. Okay, and then we're going to compute to get the power spectrum get the power spectrum. We're going to compute the Fourier transform within this gray square, the two-dimensional Fourier transform. So, okay, so first of all, the camera integrates. If we think of the laser as a pulse, so we picture this laser beam coming in, we can think of it as a pulse in time. It is a pulse in time. It's 100 nanoseconds long, this pulse. And here, let's say here's the camera. It all gets integrated onto the camera. So the camera integrates over time. So here we have the camera. This is what the camera sees. It's a function of X and Y, and it's integrated over time, over Z. Then we take the Fourier transform, two-dimensional Fourier transform of this thing. And when we do that, what we're really getting is a slice of the power spectrum, three-dimensional power spectrum, a slice in K space, because we're looking at KZ equals 0. Because you can imagine it's as if we took a three-dimensional Fourier transform and set KZ equal to 0. So this, you would see this looks like this is the KZ equals 0 element of the Fourier transform. So, okay, so we're really getting a slice. We're not losing anything. The fact that it's being integrated on the camera, that's what I'm saying. It just gives us K equals 0 in that dimension. So, okay, so to get this power spectrum, we take 200 of these images. We repeat it 200 times, which takes 7 seconds. And then we compute this ensemble average. Then we can compare this with the Bogoliubov approximation. Now, the Bogoliubov approximation would say, if we think of the waves as being small amplitude waves, then this power spectrum, the static spectral factor, should be given by 1. This is the vacuum fluctuations, the shock noise, plus these terms which are related to the population and correlations of these waves. So we can use these other terms to see the waves. Okay, so what we're gonna do is we're gonna do that experiment. We look in this plane, and we're gonna look at various distances, not just one time. It's not like the real universe where we only have one time that we can look. That's the present day. Here we can look at various times. And this is the pattern we see when we take this 2D Fourier transform and compute the power spectrum ensemble average. We see these shrinking pattern of rings. As time goes on, it's the ring pattern which shrinks, and this is the cosmological particles is what we're seeing here. And I'm going to explain why we've seen shrinking rings. And what we're seeing here is this static spectral factor, power spectrum, where m is the total number of photons. Okay, now the phase relationship, both in the real universe and in our analog experiment, the sound waves are created with a definite phase relationship, and that's why we see the pattern. And so let's see what I mean by phase relationship. Phase relationship. So at the time of creation, so this is the time of the change in the frequency, the waves are created perfectly out of phase. So it's a pair. One going to the left, that's minus k, and one going to the right, that's plus k, and they're exactly out of phase. And the reason they're exactly out of phase, it's we want no change in the density. What we're saying is we have this gas, photons, and we suddenly create waves instantaneously. When you do that, there's no time for the photons to move. At the moment you created the waves, photons don't have time to reorganize themselves into a density wave. So at the moment you've created it, you need to create it like this, where you have two waves perfectly out of phase, so there's no change in the density at the moment you created it. Then if you wait time to go by, these two waves propagate away, and now they're no longer perfectly out of phase, and then you will have a density wave after some time. So this is the definite phase relationship. It's perfectly out of phase at the moment they're created. Now, let's go to some other wavelength. This is K1, but let's go to some other wavelength, K2. It's also created perfectly out of phase, but the frequency is different. K1 and K2 have different frequencies. So at our time of observation, K2 has some other phase relationship. Maybe it's almost perfectly in phase, is what's shown here. So at the time of observation, there are waves which are going to be not perfectly in phase and other ones which are perfectly in phase. And that's what makes this ring pattern. If we start in the middle and go out, we're going, say, wave which is in phase and then out of phase. In phase, out of phase. As we go to higher and higher K, we're going to go through in phase and out of phase at the time of observation, specifically 37 picoseconds. But then if you wait longer, the longer wavelengths are going to come into phase. So if you're looking at some very low frequencies, very long wavelength, it takes a long time to come into phase. So if you wait a really long time, then you see the small rings. That's why the rings shrink. So, and this is different from the real universe. In the real universe, it's thought that the waves are created perfectly in phase. At the moment of creation, at the end of inflation, the acoustic modes are at a maximum. When those quantum fluctuations turn into the acoustic waves, it's thought to be at a maximum. So it's different. So that you could call that a contradiction between the two descriptions of the early universe. The usual description says they're in a maximum. The alternative description that we're discussing says they should be created at zero for the reason that we mentioned. For this reason, that particles didn't have time to move, it's created at a node, not an antinode. So that's the case for the early universe. So we see these shrinking rings. We could compare it with the theoretical calculation using what we discussed. We wrote the static structure factor. Here, we said the static structure factor was related to the production of these, to the population of these particles. Using an expression like this, a little bit more complicated, taking into account both quenches and everything, then one gets these red curves, which agree pretty nicely with the experimental data. So it shows we really understand how these pairs are being created. And these are what we call this acoustic peaks because it's similar to what's seen in the cosmic microwave background. So here you can compare. Here's what it looks like in the real universe, and that's what it looks like in our experiment. So it happens to be sort of similar look. So we can ask, is this spontaneous production of waves, or have they been stimulated? Were there waves before the quench, before the change in frequency, and they caused waves after the change in frequency? Or was it total vacuum before the frequency, and then it was spontaneous quantum production? So we need to know the initial state, know if it's spontaneous or stimulated. So we want the initial state, but first let's look before quench 1. We'll call this initial state the B, the population of the B operators, before the first quench. So in order to get that information, we look at the very lowest K. Now this K is so low that it doesn't have time to oscillate. It has a very, very low frequency. And so during the time of the experiment, it doesn't oscillate. So that looks back in time. We found that the low Ks are like a window back in time, because they can look, when you are over here on your camera and you look at the low Ks that appear on your camera, you're looking all the way back to here, before the second quench, before going through the cell, and before the first quench, because they don't have time to oscillate, the low Ks. So when we look down there, you'll notice that all of the low Ks are low. It's like a minimum. It's not some max. It's all a low value. That's showing that it was vacuum, because if you take the approximation of very low K, then the power spectrum should be 1 plus twice the population. So since it's a low value, close to 1, here, it's just a little bit above 1, it shows that the population was around 0.2 or less. So, so a population of 0.2, first of all, it's less than 1. So that would mean the spontaneous contribution is dominating, because the quantum contribution is like 1 or a half or something like that. So it's 0.2 quanta. So it's mostly spontaneous. And that was in the first quench. And again, that was because the reason that we got this nice quantum value is because we bought a good laser that doesn't have any waves on it before the first quench. So now let's go to the, okay, so I'll say a few more words about this first quench. It doesn't diverge, meaning if this were a thermal state, if the laser beam had a thermal distribution of photons in it, then we would expect this thing to diverge. It would look like this blue curve. Instead of this curve, it would go way up. So it's not thermal. The laser beam was not thermal. It was spontaneous because it's less than 1, as we say. Also, okay, so what we've done here is put all the curves one on top of the other. So it's the same curves as these curves, only put them all on the same graph. And then you could really see that it's some low value. And it's like 1.4. So we get 1 plus 2 times 0.2. So also the fact that it's sort of, you could say it's not diverging here at the bottom, means SFK is scale independent. That's the words they use for in the real universe. It means at low K, it doesn't diverge. It's sort of independent of K for very low K, like the CMB spectrum. Okay, so the initial state is that for the first quench. Now let's go to the second quench. It's a bit more complicated because the second quench has stimulation. First of all, we created particles in the first quench, and they're going to propagate through the cell, through the vapor cell or the gas cell, and stimulate pairs in the second quench. Also, there's spontaneous emission. This is a laser beam going through a gas. The gas absorbs the laser and then re-emits, scatters the photons. That also produces these scattered photons, which are going to hit this second quench and create pairs. So in the second quench, we see, okay, first of all, we see it's not about oscillating about unity. The static structure factor is supposed to be 1 plus. We went back to the original expression. Here, static structure factor should be, the spontaneous shot noise contribution should be 1. And then you get the other stuff due to the waves. So it should be oscillating about 1, basically. But it's not. And that. Okay, it's shifted up relative to 1. It would be like the magenta curve if there was nothing stimulating the second quench. It'd be oscillating about 1. So it shifted up. Now it's shifted up for 2 reasons. It oscillates, the shift is B plus A. It means it's the what there was before the first quench. That was, we said it was 0.2. But also there's A, which is in the glass cell. There are these spontaneously emitted photons because it's the laser beam is being scattered. So that gives the A. So that's what shifting is the spontaneous emission. The laser beam being scattered by the gas.
So it's an experimental bias, yeah, right?
Bias?
In the sense that you have created this term, but it is because of the experiment, not representing what happened in the earlier years, right? It's an extra term that is because of experiment.
Yeah, you're right. We're drifting away from the early universe. We also have two. We have first the contraction of the universe and then the expansion of the universe. That's different from the early universe also. Yes. Yeah, in the early universe, it's thought that inflation was purely quantum. So yeah. So we can prove that the spontaneous emission is what's doing, shifting this curve up. We can prove that that's it by, instead of doing this pulse, which has the nonlinear, we can turn off the nonlinear effect by making the pulse long and weak. If we make the pulse long and weak, then we get 1, the blue curve. Here's the curves I've been showing you so far. It's black. It turns into the blue curve if we make the pulse long and weak. That's because the spontaneous emission has a finite coherence time. It just leaves the it goes out of it stops being coherent after there's a broad spectrum, so it doesn't stay coherent for very long. So if you make the pulse long, it no longer has an effect. Anyway, so now, furthermore, we can show that the temperature is less than about 2 mc squared, where I'm talking about the temperature of the photons when it's in the gas. It's a very low temperature fluid. So that's why there was a question, why is it called a quantum fluid? It's because the temperature is very, very low, like less than 2 mc squared, where c is the speed of sound. So that's like an atomic Bose-Einstein condensate. It's as cold, for people who are familiar with Bose-Einstein condensate, it's just as cold as a Bose-Einstein condensate in the sense of comparing the temperature to the relevant energy scale, which is the chemical potential.
What is M here? The mass
M is the effective mass of the photon.
of the fluid.
Yeah, which in this gas. So I'll get to that in a minute. So okay, so what we found is that the spontaneous emission includes 1.2 quasi-particles per mode. So it's a flat spectrum. It's not at all a thermal kind of spectrum. It's a flat spectrum with 1.2 quasi-particles, 1.2 population of 1.2 for every mode. Now, these two quenches, these beat, they have an interference pattern. There's interference between these two quenches. You can see that here. You can sort of see a beating pattern. I hope you can see that. That's good. Fat and narrow, fat and narrow. And that's because when the frequency here inside the cell times the effective time is an integer multiple of pi over 2, then you're either going to get a node or an antinode. That's what causes these. And we can put these points. We get K. We know the frequency from this expression. K, we read off this graph of the power spectrum. And we can put the points and they fall nicely on the dispersion relation. We can also look at individual modes. So here we put all these different power spectra, one above the other at the various times. And then we just follow along one K value. And look at the various values of the power spectra, and we see that it oscillates in time sinusoidally. And these oscillations also fall nicely on the power spectrum here, this black curve. Are they're fitting as sine waves to these oscillations. So now I'm going to explain that the system is really 3 + 1 dimensions. This looks like 2D. We have a laser beam, we have these planes where we're looking at the oscillations in x, y, and then as a function of time or z. But it's really 3-dimensional because true time is another dimension. So there's really 4 dimensions here. There's x, y, z, and t as z is playing the role of time, and time is playing like another z. It's playing z and time are exchanged. So in order to understand that, okay, this is the Gross-Pitayevsky equation. Okay, let's start from the beginning. This is the equation describing our system. This is the wave equation within the paraxial approximation and slowly varying envelope. We assume that the electric field is changing slowly, and it's also small angles, paraxial. We could change coordinates here. Instead of time, we're going to go to z prime. Z prime is a co-moving coordinate, co-moving at the group velocity. So here's a laser pulse. Here's a pulse that we produce with our laser beam moving along. We go into the z prime coordinate where the pulse is not moving. In this coordinate system, the pulse will stand still, and it will also be compressed by some factor here related to the it's related to the group velocity dispersion. So anyway, I don't want to get too much into that, but it's related to this quantity here, that the second derivative of the frequency is a function of the wavelength. So if one makes this change a variable, one ends up with this equation, which is the 3-dimensional Gross-Pitayevsky equation, which is exactly like in an atomic Bose-Einstein condensate, where you have a 3 dimensions plus time. So, okay, so this system that we see, this laser beam, is actually evolving in true time, and that's why we have this extra dimension. We could also take go from the power spectrum to the correlation function, the density correlation function. They're related. The power spectrum is related to the density two-body correlation function by this Fourier transform. We could do that Fourier transform, and we get these density correlation plots, which show that the correlations extend to larger and larger distances. So it starts out here at short distances and gets to larger and larger distances as in other words, at the moment of the quench, we're making these pairs of waves, and then they move, causing correlations over longer and longer distance lengths here. And I'll skip this one. It's similar to an article, and we can reproduce their calculation using our technique of just using this very simple expression to calculate the density correlation function. So we can compare now back to the early universe. Here are our waves where we change the K scale a little bit so they all have a maximum in the same place at the same K value. It looks similar to the Planck spectrum and to the spectrum from the Planck collaboration, the CMB acoustic peaks. And So now, this is also, this multipole L, the maps to K. This can be thought of as K. There's an article which explains that. That in the early universe, what we're seeing is K, is the wave number. So now let's compare and contrast our experiment with the early universe. First of all, the oscillations are due to a well-defined initial phase. That's true for both cases discussed. These pairs are produced with a certain phase. But it was pi over 2 for the real universe, whereas it's pi for us. Or pi for the alternative description of the real universe. So there's some tension there in the descriptions of the early universe. Now the decay, okay, I didn't mention that, but these waves damp away. In both our experiment, the oscillations get smaller, and in the real unit, the CMB, they also get smaller. They get smaller for different reasons. For us, it's just the Bogoliubov coefficient gets smaller. When you go out to big K, there's less mode mixing. In the real universe, it's photon diffusion. That's why the waves damp away for large multipole. Photon diffusion as they travel through the space-time to the present. In both cases, there's a scale invariant region due to quantum fluctuation. So it means here at low K, this is considered flat. It looks very small here on this scale, but one can stretch this graph and see that it's flat here. And ours is also flat. And this is called scale invariant. And it's scale invariant for different reasons. Ours is scale invariant because we had a shot noise limited laser. We said early K's is a window back in time. Small K's was a window back to early times where we had our shot noise limited laser. In the real universe, it was the red shifting during inflation that made it vacuum. They said all the modes red shifted to nothing. This is probably, I don't know if this is interesting to this audience, but we compare our quantum fluid of light with what one can do with an atomic Bose-Einstein condensate. And we had the quantum fluid of light has the disadvantage that it has a limited effective time of evolution. We had quenches. That's great for this fluid of light. You might say, oh, we can simulate anything with this fluid of light. It's not true because it doesn't last very long. You can only do something that happens very fast. You can't watch it evolve for a long time. Unlike a Bose-Einstein condensate, which you can do that. But this quantum fluid of light has an amazing signal to noise. And we saw these beautiful images. The density fluctuation that you're seeing in this image is like a 10 to the minus 3, 1 part in 1,000 on top of the intensity of the laser beam. So when we say there are waves in the intensity of the laser beam, they're very slight waves. Bose-Einstein condensate, you can't come close to. It takes a lot of data to do that, as I'll show in next week's colloquium. But anyway, the quantum fluid of light has superior signal to noise due to the fact that you really image the particles directly on the camera. In a Bose-Einstein condensate, you have to take pictures of the atoms. Here, the particles come and hit the camera. You really directly image the particles. So anyway, and it's also a huge number of photons. So for example, here's the experiment that I've just been showing you. Here's our power spectrum showing these acoustic peaks. Here's the real thing. And here's what you could do in a Bose-Einstein condensate. This is what was reported. We have very few points and there's a lot of noise. It's hard to see the oscillation. So the photon gas does better in this sense for this particular experiment. So in conclusion, we observe analog cosmological particle creation in the fluid of light. We quantitatively confirm the quantum field theoretical prediction. We had a very good agreement between the theory and the experiment. We saw that the pair production is spontaneous in the first quench and stimulated in the second quench. We saw that the long wavelengths provided a window back in time, and the quantum fluid of light is really quantum. It's very cold. It's as cold as an atomic Bose-Einstein condensate. Thank you.
We have time for 1, 2 questions.
Theory and lab work.
Me personally, I did the simple version of the theory, and then the students did the more sophisticated, where they took into account absorption. My group, this was a sabbatical, so I was in someone else's group. But so I sort of, you could say, designed the experiment, but the whole group really took it and took it away.
Right.
Yeah, it was fun.
Questions? I guess it's more generic question about these analog systems, so, which is, I mean, not this is just a question that I'm curious about. So, what do you think can we learn from this actually? Do you think we can learn something new from the early universe with these experiments? Or is, of course, it's nice to see, but do you think we could learn something new?
Okay, well, for this experiment,
Yeah.
it's not, every experiment is different, but for this particular experiment, what did we learn? Good question. I think thinking about, we learned the idea of the phase relationship that I think it calls into question the idea that the acoustic modes are produced with a perfectly at a maximum. It makes much more sense, I think, to say that they're produced at a node, and then they start to evolve, and so that's one issue. Another issue is I think it verifies that these acoustic peaks really could come from this type of production that we're seeing, because to me, the description, when I explained to you the microscopic description at the very beginning, with the many steps and the modes becoming frozen and unfrozen, and the quantum fluctuations turning into acoustic waves once the plasma is created, to me, that's a lot of steps. And people, I guess, are sure, they know more about it than I do, but to me, it seems like it's nice to have some kind of confirmation, some kind of analog experiment that this type of pattern that we see can actually be created.
I agree.
Do you actually know about some reason why they assume that they are created in phase?
I mean, a maximum.
Yeah.
No, it was just somehow the frozen in modes exist, and they're at their I can't really explain it other than just hand waving, but they.
I comment that maybe I think the most accepted vision now is that quantum decoherence. So it's like effects from the environment that put them in phase on the super horizon scale. I never understood. I just telling you, I am not 100% convinced by that, but it seems that people in the topic are.
Okay, yeah, I would feel much more comfortable if they finally decided they're out of phase, and I would feel really good about that.
But I think we're going to send it this to make possible, to discard one or the other, or not. This question of whether they're at a maximum or not.
I'm sorry, and what about that?
Where, with this kind of experiments or with something you can actually tell, like, is this and not that case.
Well, I think it just points out, doing the experiment and thinking about the experiment, points out how logical it would be if they were out of phase. It doesn't actually prove what happened in the early universe.
Yeah, because we don't know if it was out of phase or in phase, right?
Yeah,
So
I-
what you are saying with this experiment is that if it wasn't in phase, if it wasn't maximum, we could still have this observation. We can reproduce the observation with these initial conditions.
We might,
Yeah.
without a phase.
Yes.
I think that okay, well, I think they adjust 6 parameters in order to max the CMB spectrum. They have various adjustable parameters.
Mhm.
Now, if they said it was out of phase, would they be able to then adjust their parameters and match? I don't know.
Okay.
Yeah, maybe. So the volume coefficient, you can also use them to compute, for example, the Unruh effect and the Hawking temperature.
Right.
And so could you have an application of your experiment to this thing?
Okay, yes, that's what I'm gonna discuss next week. With the
yeah,
Bose-Einstein
yeah.
condensate, I saw the Hawking radiation.
Yeah, with the same thing of the Bogoliubov coefficient, I guess.
Yes, and there are Bogoliubov coefficients definitely involved.
If you enjoyed the video, like and subscribe.